Yeah, good evening, students. Good evening and good afternoon to one and all. I hope you are all good and safe. Can you all able to see me? Am I visible and audible to all of you? Good afternoon. Good afternoon, students. Am I visible and audible? Yes. Okay. Okay. Good. So let's start with the new lesson today. So we have completed 2 lessons, right? GOC and hydrocarbons we have completed. And then today's session, we are going to start with the P block elements of group 13 and group 14. Okay. Yeah, good afternoon, Hashira. Good afternoon. Okay. So let's start with the class. So here is the periodic table. So in this periodic table, you can see there are 4 blocks, right? So what are the 4 blocks of the periodic table? They are S block, P block, T block, and F block, right? So this is your S block and this is the P block. And there are 18 groups and 7 periods in our periodic table. And the P block consists of group 13 to group 18. Okay. So group 13 to 18 consists of the P block elements. And coming to the general electronic configuration of P block element, it is NS2 NP126. NS2 NP126. Why those elements are called as P block elements? Why the group 13 to 18 elements are called as P block? Because the last electron enters into the P orbital. That's why we are calling those elements as P block elements. Okay. So for boron group, it is NS2 NP1. For carbon group, it is NS2 NP2. So like that, it goes on till the 18th group. Okay. So those electronic configuration I will discuss with you all in the upcoming slides. Okay. So, but there is an exception, you see. Exception is helium. Helium is not a P block because the electronic configuration for helium is 1s2, right? The last electron enters into the s orbital, not the p orbital. But it is placed under the inert gases. Okay, it is also inert in nature like neon argon. So that's why we have placed helium in the neon argon group. Okay, but it is not the P block element. Got it? So with this helium as an exception, the remaining elements are called as P block elements. So taking this group 13 to group 18 elements alone, so we have group 13, 14, 15, 16, 17 and 18. So totally we have 6 groups in the P block elements. Okay. So in your class 11, you will be studying the group 13 and group 14 elements. And in your class 12, you will study about the group 15 till 18 elements. Okay. So here in this lesson, we are going to deal with group 13 element, that is boron group. And the next one is group 14, that is carbon group. Okay. So only these 2 groups we are going to discuss here in this class 11 session. Okay. So talking about the boron family. So let us discuss one by one. We will go with one by one family. Okay. So first family is boron family and the second family is carbon family. So moving on to the boron family. So in this boron family, so we have different topics. We have many topics here in this family, which you can see in your NCERT book. But some of the topics are deleted from this lesson. Okay. So those topics are the compounds of boron and the compounds of carbon. So that compounds part is deleted. Rest all is there for your JEE and NEET. Okay. So the topics that we are going to cover in this topic and the topics that we are going to study for our competitive exams are the introduction, the trends in general properties, and the properties of group 13 elements. Properties, general properties means something related to kind of oxidation state and size, etc. Okay. And coming to this property, the third topic, there we will study about the chemical properties, general chemical properties of group 13 elements. And the fourth topic is the anomalous behavior of boron. So anomalous means unique. Okay. So the unique nature of boron we will study there in that fourth topic. Got it? So we can move on to the introduction. Coming to the introduction to boron family. So for first letter, we should know the elements that are present in that boron family, right? So those are boron, aluminium, gallium, indium, thallium, and nihonium. So these are the 6 elements that are coming under group 13, that is boron family. Okay. So the general electronic configuration for this particular group is Ns2, Np1. Ns2, Np1. And boron is a very, very rare element. Boron is a fairly rare element, but we can find boron in orthoboric acid. Okay. And in borax, we can find boron, and in kernite also boron is present. So boron is present in all these 3 compounds. Okay. So now borax, this particular borax, the second compound that you can see on the screen, that borax, it occurs in the Puga Valley and Sambar Lake, which are there in Ladakh and Rajasthan region. And aluminium is the most abundant metal and the 3rd most abundant element in the earth crust. So this is very important. So which is the 3rd most abundant element in the earth crust means you have to go for aluminium. Okay, it is one of the very important ones. So this is the general introduction to boron family. I hope this is clear to all of you. So now we will move on to the electronic configurations of group 13. Electronic configurations of group 13 elements. So let me show the elements. They are boron, aluminium, gallium, indium, thallium, and nihonium. So first of all, you have to memorize all these elements. So without memorizing the elements, you will not be able to attend the questions. Okay. So most of the questions will be like you have to arrange them in increasing or decreasing order of size, ionization energy. So like that, they will ask you to arrange the elements, or they will ask you to find out the increasing or decreasing order of the corresponding property. So for that, you need to know the elements and its order. Okay. So just memorize these elements. And coming to the general electronic configuration of boron. So as I have already told you, the general electronic configuration is Ns2, Np1. Okay. So this N represents the principal quantum number or the period number, we can say. So boron belongs to which period? It belongs to 2nd period. So the electronic configuration would be 2s2, 2p1. And for aluminium, it is 3s2, 3p1. For gallium, it is 4s2, 3d10 and 4p1. 4s2, 3d10 and 4p1. So the 3d orbitals, if you see, they are little higher in energy compared to 4s orbital. That's why it is coming next to 4s. Okay. And d orbitals are completely filled. Okay. D orbitals are fully filled for gallium. From gallium, d orbitals would be fully filled. So the configuration would be 4s2, 3d10 and 4p1. And for indium, it is 5s2, 4d10 and 5p1. For thallium, we have both d orbital as well as f orbital. Okay, 4f orbital as well as 5d orbital we have for thallium. And in the 6th shell, we have 6s2 and 6p1. That is the configuration. And coming to nihonium, 5f and 6d orbitals are filled for nihonium. And nihonium is a radioactive element. It is one of the radioactive element which is present in this group. Okay. So this is about the electronic configuration. So for boron and aluminium, we don't have d orbital. Coming to gallium and indium, we have fully filled d orbitals present inside the thing. And for thallium and nihonium, we have both f orbital as well as d orbital in the filled form. Okay. So this is what you have to keep in mind for electronic configuration. So now next we will go with the trends in the general properties. Trend. So across the period and moving down the group, what is going to be the trend for corresponding periods of this group 30? That we will discuss. Okay. So the first property that we are going to see is atomic size. So we are going to see the trends in atomic size first. So let me show you the graph for that. So here is the graph. So the x-axis is atomic number and y-axis is atomic size in picometer. Okay. So let me go with this. So this is the trend that is being observed for boron family. Okay. The atomic number for boron is 5, right? So the first element is boron. Next aluminium, gallium, indium, thallium. Okay, nihonium is radioactive, so we will not study about the nihonium. Okay, it will not be studied. Okay, chemistry, the study of chemistry is very difficult for nihonium as it is radioactive. So we will not consider that. Now, if you see the trend is increasing. Atomic size is increasing from boron till thallium, right? So from boron till thallium, atomic size is increasing. But there is an exception between aluminium and gallium. You see here. So first it increases from 88 picometer to 143. But again it decreases, then it increasing. So you see here, there is an exception observed for this aluminium and gallium. Okay. So why? Why this exception? It is due to the poor screening of 3D subshell. So just now we have seen, no, for gallium, we have 3D orbitals. We have 3D10 configuration. So those d orbital electrons, they will not shield the outer electron properly. Okay, they have very poor shielding effect. Suppose if this is the nucleus and this is shell number 1 and this is shell number 2 and if this is shell number 3 and if this is shell number 4, here for gallium, the outermost gallium belongs to 4th period. So we will have 4s2 and 4p1 with the 3d10 configuration for gallium, right? So, excuse me, sorry. So in 4s orbital, we have 2 electrons and in 4p orbital, we have 1 electron. But there are electrons in 3D also. Here also we have 3D orbital. In that we have 10 electrons. So these 3D electrons is not shielding this s electron and p electron properly. So what happens? So more gaps will occur here. The last electron which are there in the s and p orbital, they will be attracted towards the nucleus. So the size will get decreased because of the contraction. Got it? What am I saying is clear to all of you? So the d electrons, they have poor shielding effect or poor screening effect. Because of this, the outermost electron is getting attracted towards the nucleus and the size decreases because of the attraction due to contraction. Clear? If you're having any doubt, you just ask me. Okay. So because of this poor shielding of 3D subshell electrons, the effective nuclear charge is present inside the nucleus. So that effective nuclear charge increases. Okay. So what happens because of this? The size of the aluminium is greater than the size of gallium. Okay. Size of aluminium is going to be greater than the gallium. Okay. When you see for indium and thallium, they are approximately, they are in similar size, 167 picometer and 170 picometer. They are of almost similar size. It is due to the inert pair effect. Okay, due to the inert pair effect, effective nuclear charge increases and both are having approximately similar size. Not exactly same, approximately they are similar. So what is the general trend that is being observed for group 13 elements for size? It is this. Boron, then your gallium, then comes aluminium, then indium and thallium, they are almost similar in size. So if in the exam, they are asking to find out the correct order of size for group 13 elements, you have to go for the option in which you have this order. Okay. So here the exception is due to the poor shading of 3D subshell. Got it? Shall we go with the next property? Is the atomic size property clear to all of you? If it is clear, just type yes in the chat box. Shall we go with the next properties? Yes. Okay. Thank you, Sushma. So we will go with the next property, that is ionization energy. What is ionization energy? The energy, thank you, Shamila. Thank you. Good. Yes. The energy required to remove the outermost electron in an isolated gaseous atom is called as ionization energy. Right. So what is the trend that is going to be observed for this? Atomic size and ionization energy, they are inversely proportional to each other. Right. So all these concepts you might have studied in your periodic classification of elements lesson in your school. Okay. So we will also discuss that. So let me go with this. Yeah, again a graph with atomic number and ionization energy. Okay. So the trend is, here is boron, aluminium, gallium, indium, and thallium. Okay. So you see here, actual trend is the ionization energy should decrease on moving down the group. But there is an exception again for this aluminium and gallium. So why this exception arises? The same reason. There the size is getting decreased, no, from aluminium to gallium. So now ionization is getting increased. Since they are inversely proportional, there is an exception observed here for the same two elements for the same reason. Poor screening effect of the 3D subshell. Effective nuclear charge increases and the energy required to remove the electron from the gallium is more compared to aluminium. Okay. So the size of aluminium is greater compared to the size of gallium, right? So gallium is very small in size. So the outermost electron is closer towards the nucleus for gallium. So if you want to remove this electron, you need to supply more energy. So that's why gallium is having the higher ionization enthalpy compared to aluminium. Not very much, but there is the 2-unit differences there. Okay. So this is the reason. Again, coming to indium and thallium, if you see, actually it should decrease, but it is increasing. The same reason. Due to the inert pair effect, this effect is arising. Now the trend is this. Boron will have the highest ionization energy value, then thallium, then gallium, aluminium, and indium. Okay. So all these are the orders observed for group 13 elements. So you need to study this particular trend for ionization energy for group 13. Okay. So just learn that alone. The trend alone you have to study. If they are asking you the reason, then go for the poor screening and inert pair effect reason. That's all. Okay. Nothing to worry about it. Now we will go with the third trend, that is electronegativity. So what is electronegativity? So two atoms are bonded with each other. One electron would be from atom A and another electron will be from atom B. So the tendency of a particular atom to attract the shared pair of electron towards itself is called as electronegativity, right? So this is atom A and this is atom B. Two electrons are there. And let me take atom B is more electronegative. Okay. So if atom B is more electronegative, it has the tendency to pull the shared pair of electron towards itself. That is called as electronegativity. Okay. Now what is the trend observed for group 13? So again we will take a graph. So here is boron. The electronegative value for boron is 2. Aluminium is 1.5. Gallium 1.6, 1.7 and 1.8. So actually atomic size is inversely proportional to ionization energy and it is inversely proportional to electronegativity also. Okay. If on moving down the group, if size increases, ionization energy should decrease. So that's why it has got decreased in the previous thing. Now electronegativity also should get decreased. But you see, from boron to aluminium, it is decreasing. Again, it increasing. So it is irregular, right? So there is an irregular trend observed for this. So why there is an irregular trend for this aluminium till thallium? It is also due to the poor shielding of d electrons and f electrons. Due to the poor shielding of d and f subshell, effective nuclear charge is getting increased and electronegativity is increasing down the group. Electronegativity is increasing down the group. Just a second. Yeah. Coming to the electronegativity trend for these elements. So boron is highly electronegative in nature. Then you have to come from the last. So after this boron, we have thallium, right? Thallium is 1.8. So after boron, thallium, then indium, gallium, and aluminium. So aluminium is the least electronegative element in its group. Okay. So these are the general trends in the general properties of group 13 elements. Okay. Atomic size, ionization energy, and electronegativity. So for group 13 elements, the trend would be entirely different. You have to study all the 3 trends that is being observed. Okay. So any doubt from these trend in the general properties? Do you have any doubt in the 3 properties? If you're having any doubt, you can let me know. Otherwise, we can jump to the properties of group 13. Shall we start with the properties, students? Properties of group 13. Say yes or no. Okay. Okay, thank you. So properties of group 13. Okay, thank you so much. So coming to the property, first we will discuss about the physical properties of group 13 elements. So physical property in the sense the appearance and melting point, boiling point, its color and its physical state, etc. Right? So those things we will discuss. So first I will talk about the boron. Boron is a non-metal. Boron is non-metallic and it is extremely hard and a black colored solid. Okay, so this is boron. It is the only non-metal that is present in the group 13. Okay, so it is non-metal, extremely hard and black colored solid. And it is having very strong crystalline lattice. Boron has unusually high melting point. So because of its very small size, they form a very strong crystalline lattice, due to which the melting point is going to be very, very high. Okay. Rest of the members of the group 13, rest of the members in the sense from aluminium till thallium, they are soft. Only boron is hard. Rest others are soft. Rest of the members are soft metals with low melting point and high electrical conductivity. So conductivity is very high for the other elements. Okay. Melting point is very less for the other elements, but conductivity, electrical conductivity is very, very high. Suppose if I want to talk about one of the member of group 13, except boron, let me take gallium. Gallium has a very low melting point. Okay, very low melting point. You see 303 Kelvin, but high boiling point. Boiling point is exceeding 2000 Kelvin. So it is above 2500, 2676 Kelvin is extremely high. Okay, boiling point is very high, but the melting point is very, very less. Okay, so if you just keep in your hand, see, you see that gallium metal is getting melted. Okay, so it will melt. Gallium will melt at very low temperature. Now coming to density, so on moving down the group, mass increases. Right? If mass increases, density is equal to mass by volume. So density also increases. Density of the elements increases on moving down the group. Okay. So these are the 5 points you have to keep in mind about the physical properties of group 13. Okay. So the hardness, boron is hard, others are soft, and the conductivity, melting point thing you keep in mind. And for this gallium, boiling point is very high and melting point is very low. Okay. So now we will go with the other properties. Some of the general chemical properties we will discuss now. The first is the oxidation state and chemical reactivity of group 13. Okay. So these are the group 13 elements. Coming to the topic, boron is extremely small in size. On moving down, the group size increases, right? So boron is the only element which is very small in size. If the size is very small, ionization energy is very high because they are inversely proportional. So boron always forms covalent bond, like in case of BF3. So let me take BF3. It is a molecule. Okay. So in this BF3 compound, boron will form the covalent bond with fluorine. Okay. Since it is very small, it can form covalent bond. Okay. And coming to aluminium, it is more electropositive in nature. Electropositive means it can exist in Al3+ form more easily. Okay. It shows oxidation state of +3. So it is more electropositive. It can able to lose its electron more easily compared to boron. Okay. And coming to gallium, gallium is also electropositive and it shows oxidation state +3. And indium, it is not that much electropositive, but it shows +3 and +1 state also. Aluminium, gallium will not form +1, but indium will show +1. And coming to thallium, it only shows +1 oxidation state due to the poor screening by 4f and 5d subshell electrons. So, what do we get from this? The stability of lower oxidation state increases on moving down the group. The stability of lower oxidation state increases on moving down the group. So, aluminum is in +3, gallium is also having +3, but here it is +3 as well as +1, but here it is +1. So, lower oxidation states are becoming more stable on moving down the group due to inert pair effect. Okay. So, the relative stability of +1 oxidation state increases down the group. So, we are following this order for oxidation state. So, what is inert pair effect? What is inert pair effect? So, the reluctance of s electron to take part in bonding is called as inert pair effect. Okay. So, let me explain you. So, this is the nucleus. So, if I want to talk about indium, so let me, okay, I'll talk about indium. So, for indium, the outermost shell is 5th shell. So, 1, 2, 3, 4, 5. So, in the 5th shell, we have 5s2 and 5p1, right? 5s2 and 5p1. So, this is the thing. Now, in the 4th shell and 3rd shell, we have d electrons and f electrons. In the 4th shell, we have 4f electrons for indium and we have d electrons for 3d electrons for indium in the 3rd shell. Now, these d electrons and f electrons, they will not shield. They have very poor shielding effect, right? So, they will not shield the outermost electron properly. So, because of this, these two s electrons, they will get attracted towards the nucleus. Okay. So, if they are getting attracted towards the nucleus, they will not be able to form the bond with the other element from outside. Okay. So, these two electrons, they are inert in nature. They are not able to form the bond. They are not able to react with other element. So, they are getting inert. So, only the electron which is there in the p orbital, the electron which is there in the p orbital, only this electron can go and form the bond. Either it can form the covalent bond or it can form the ionic bond. So, only one electron can be donated. So, indium and thallium, if you see, they are stable only at +1 oxidation state. The reluctance of s electron to take part in bonding is called as inert pair effect. And this is the reason. Poor screening of 4f and 5. Okay. So, this is what you have to keep in mind. Now, we will continue this topic. +3 oxidation state is highly oxidizing in nature. Okay, they are highly oxidizing in nature. Oxidizing means they have the capacity to gain the electron. It's called as oxidizing. Okay, and the compounds in +1 oxidation state are more ionic than those in +3. Suppose if I want to talk about this thallium, because thallium can exist only in +1 oxidation state, right? So in thallium chloride, here it is plus and minus, and here it is 3 plus and 3Cl minus. So here in this compound, it is in +1 and here it is +3. So +1 oxidation state, this compound is more ionic compared to TlCl3. Okay, lower oxidation states are more ionic than the higher oxidation state containing compound. And coming to boron and aluminium, they form trivalent compounds which are electron deficient. Boron and aluminium, very important point, which will be used for the whole entire chemistry. Okay. So they form the covalent compounds, which are electron deficient in nature. I'll show you. So here is the boron compound, which is BH3. And boron has one empty p orbital in it. Boron has one empty p orbital in it. And the hybridization of boron is sp2. Hybridization of boron is sp2. If the hybridization is sp2, then the geometry is planar. I will tell you how to find out the hybridization and all later in the chemical bonding lesson. Okay, you don't have to worry. So the hybridization is sp2 and the geometry is trigonal planar. Planar means all the 4 atoms, that one boron and 3 hydrogen, all those 4 atoms are lying on the same plane, and the empty p orbital is perpendicular. Empty p orbital is perpendicular to this plane. Okay. Now this particular BH3 compound is now going to get interacted with NH3. NH3 is ammonia. Okay. So nitrogen has one lone pair of electrons in it. So that will act as an electron rich center. So this filled electron of nitrogen goes and forms the bond with the empty p orbital of boron, and they form a compound like this. Okay, and this is called as borane ammonia adduct. Borane ammonia adduct. Now, in this borane ammonia adduct, the hybridization of boron is sp3. If the hybridization is sp3, geometry is tetrahedral. So you see here, the geometry that is being formed by this boron is tetrahedral in nature. But here it is trigonal planar in nature. Okay. So when hybridization is changing, geometry also changes. Now here, boron is gaining the electron from nitrogen, right? Boron is electron deficient. That's why it is gaining the electron from the other atom. Okay. So this reaction shows that boron forms covalent compounds which are electron deficient in nature. Got it? So I hope this is clear to all of you. Is this clear? Shall we go with the next slide? Just give me a thumbs up or respond me in the chat box. Hybridization, geometry, those are very, very important. Okay. Did you all got the concept? Have you all noted it down? Yes. Coming to the next thing, aluminium chloride. Yeah, thank you so much, students. Aluminium chloride achieves the stability by forming a dimer. You want me to explain once again? Which point? The last point? Or the entire slide? Okay, the last point I'll explain to you. Boron compounds are electron deficient in nature. Okay, they are electron deficient because of the presence of empty p orbital in it. P orbital shape is dumbbell, right? So that is the p orbital which you can see. This is the empty p orbital of boron. And to this empty p orbital, the filled orbital of nitrogen is forming the bond. So now here BH3 is electron deficient in nature. So that's why here it is accepting the electron. So that's why electron deficient, the boron is accepting the electrons from the nitrogen and it is forming the compound with NH3. Clear? If a compound contains empty orbital in it, then we call that compound as electron deficient compound. So BH3, BF3, AlCl3, all these compounds are electron deficient in nature. So we have discussed hydrocarbons also, right? In hydrocarbons, we have studied about the electrophilic substitution reaction at last. So in that, 5 electrophilic substitution, if you have noticed, in halogenation, Friedel-Crafts alkylation and in Friedel-Crafts acylation, we have used anhydrous AlCl3 as one of the compound, right? If I want to talk about halogenation, we used Cl2 with anhydrous AlCl3, right? So why we used anhydrous AlCl3? Because when this Cl2 reacts with AlCl3, so since AlCl3 is an electron deficient compound, it will accept electrons. It will accept the electrons from this chlorine and it will form the bond. Now here it is acting as an electron acceptor, which are electron deficient in nature. Okay. So the same thing is for boron also. Boron aluminium compounds are electron deficient in nature. They will always accept the electron. Is that clear for Shivashankar? Shivashankar, the students who are sitting behind the Shivashankar ID, is that clear? Yeah. Fine. AlCl3 achieves the stability by forming a dimer. So how do they form a dimer? AlCl3 is a monomer. Dimer is Al2 and Cl6. So if I take two AlCl3 together, they will form a dimer. So the chlorine will form the bond with aluminium and the chlorine from the other molecule will form the bond with this aluminium and they are forming a dimer. So this is the dimeric structure. And here if you see the chlorine aluminium chlorine bond angle, it is 118 degree. And inside if you see it is 79. Okay. And coming to the aluminium, terminal aluminium chlorine bond length, it is 206 picometer. And the internal aluminium chlorine bond length is 221 picometer. Okay. So now these trichlorides on hydrolysis in water, they form the tetrahedral type of compound. Okay. So I will take a trichloride. I will take BCl3. BCl3 is a trichloride. Now let us see the reaction with BCl3 and water. When this trichloride reacts with water, it forms boron tetrahydroxido compound with the release of HCl and H+. Okay. Now, aluminium chloride in acidified aqueous solution, it forms octahedral complex. Aluminium chloride is AlCl3, right? When AlCl3 is treated with acidified aqueous solution, they forms octahedral complex of this type. I'll show you the reaction also. When AlCl3 reacts with H2O, it takes 6 H2O molecules, which is octahedral in nature. If six ligands, all these ligands concept I will teach you in the next class 12. Okay. So if 6 molecules are coordinated with one atom, then we will tell the geometry of that particular system as octahedral. Okay. So they are forming an octahedral type of complex, and the 3 chloride ions are going out. So these two reactions are very, very important. When BCl3 reacts with water, it can take only 4 OH, and when AlCl3 reacts with water, it can take 6 H2O. Okay. The reason for this we will discuss in the anomalous nature of boron. Okay, I will tell you why boron is taking only 4 but aluminum is taking 6 ligands. That I will discuss in the anomalous property of boron. Okay. Now we will go with one question. Aluminium chloride is an electron deficient compound, but aluminium fluoride is not. Give reason. Why AlCl3 is an electron deficient, but AlF3 is not? Because AlF3 is an ionic compound. If it is ionic, the electronic configuration for aluminium in a 3+ state is 1s to 2s to 2p6, right? The general electronic configuration for aluminium will be 1s2, 2s2, 2p6, 3s2, and 3p1, right? When aluminium loses its 3 electrons, it will take this configuration. Now, when fluorine gains 1, what is the configuration for fluorine? It is 1s2, 2s2, and 2p5. When fluorine gains 1 electron, it attains this particular configuration, 2p6 configuration. Now, when aluminium loses its electron, it is attaining the octet, and when fluorine is gaining the electron, it is attaining the octet configuration. They are attaining the complete octet configuration. So that's why aluminium prefers to lose its electron when it tries to form the bond with fluorine. But AlCl3 is a covalent compound. It forms covalent bond. Covalent bonds are formed by the sharing of electrons. Ionic bond is formed by the transfer of electron. Covalent bond is formed by the sharing of electrons. So the 6 electrons are present in the valence shell of aluminium, because we have 3 bonds, right? We have 3 bonds, and each bond contains 2 electrons, and we will have 6 electrons around this aluminium. So because aluminium is a covalent compound, empty p orbital will be there. Empty p orbital will be there for aluminium. That's why it is electron deficient in nature. But in case of this AlF3, p orbitals are not empty. So they are ionic compound, and they are electron precise in nature. Okay. So this is about the thing. Now coming to the properties again of group 13 elements. General chemical properties of group 13 elements. So first we will discuss the reaction with air. Reaction with air. So air contains oxygen, right? So if a group 13 element, this E represents the group 13 element. If group 13 element reacts with oxygen, it forms the oxide of type E2O3. Okay. Air also contains nitrogen in it, right? So when group 13 element reacts with nitrogen, it forms nitride of formula En. Okay, it forms oxide of this particular formula and nitride of this particular formula. But boron is unreactive. Boron is unreactive in crystalline form. So two different forms are there. One is crystalline form and the other one is amorphous form. In crystalline form, boron will not react. It is unreactive. Okay. Now talking about the aluminium, aluminium forms a very thin oxide layer on the surface which protects the metal from further attack. So if this is aluminium block, when aluminium reacts with oxygen, it forms aluminium oxide. So an oxide layer would be formed around this. An oxide layer would be formed around this. And if any other element tries to come and react with this aluminium, it cannot react because it has the oxide layer in it. So the direct contact will not happen. Okay. And about the amorphous boron and aluminium, I told you, no, amorphous compounds, amorphous boron is reactive. Only crystalline boron is unreactive. Amorphous boron and aluminium, when they heat it up in air, they form B2O3 and Al2O3 respectively. And all other oxides are here. B2O3 is acidic in nature. Aluminium oxide and gallium oxides are amphoteric in nature. What is meant by amphoteric? They can react as an acid as well as a base. Okay. And indium oxide and thallium oxides are basic in nature. Okay. This point is very important. Only B2O3 is acidic. The other two are amphoteric and the last two are basic. Okay. This is the reaction with air, as air contains oxygen and nitrogen. Clear? Any doubt you have, students, from this reaction with air? Is this clear? P-block element is an inorganic chemistry lesson. So inorganic chemistry consists of a lot of information. Okay, with reaction, you have a lot of information. So we have to study all the informations that is given in inorganic chemistry. So in organic chemistry, if you study the mechanism, you can do the thing for, you can find out the compound or you can find out the product if you know the mechanism, if compounds are given to you. But for inorganic, you need to memorize or you need to learn a lot of information. Okay, so it is a kind of informatory thing. So I hope this reaction with air is clear to all of you. Shall we go with the next reaction? Say yes or no? Yes. Okay, Anjanashree. We'll go with the reaction with acids and alkali. So boron does not react with acids and alkalis even at moderate condition. Boron is unreactive in most of the case. So it is not reacting with alkali means base. Alkali means base, okay? So HCl is an acid and NaOH is a base, right? So boron will not react with both of them at moderate condition. And aluminium dissolves in very dilute HCl and it liberates the dihydrogen gas. I'll show you the reaction. So you see here, when aluminium reacts with the dilute HCl, which is in aqueous form, it releases hydrogen gas. It is getting evolved and Al3 plus Cl minus ions are formed. Okay. And aluminium also reacts with aqueous alkali. So first, here aluminium is reacting with acid. And in this reaction, aluminium is going to react with a base. Okay. So here is the reaction. So sodium hydroxide is a base. It is in aqueous form. Okay. When it tries to react with that base in presence of water, it forms a coordination complex. Na plus AlOH4 minus. And the name of this complex is sodium tetrahydroxyaluminate 3. Sodium tetra, and this is called as hydroxyaluminate, and the oxidation state of aluminium is 3. Okay. So this kind of compound, coordination compound is formed when aluminium is reacting with a base or an alkali. Okay. So these two reactions are very important. And moving on to the third reaction, that is reaction with halogens. So halogens, who are the halogens? Fluorine, chlorine, bromine and iodine. They are halogens, right? So when the group 13 element reacts with halogen, so we denote halogen like X. Okay, halogens are denoted by the letter X. So when it reacts with that, it forms halides of formula EX3. EX3 type of halides are formed like BF3, BCl3, AlCl3. So all these are the halides of group 13. But we don't have thallium iodide. Why thallium iodide does not exist? Due to the high ionization energy of thallium and the low electron affinity of iodine. The energy required to remove the electron from thallium is very high. Okay, so that's why it does not exist in TLI3 form. And also we have seen no thallium exists. Thallium compounds are stable only at +1 oxidation state. But here you see thallium is in +3 oxidation state. So that's why it does not exist. And the monomeric trihalides, if you see, they are electron deficient in nature. Monomeric trihalides are BF3, AlCl3. These compounds are monomeric trihalides. They are electron deficient in nature. All the electron deficient compounds are called as Lewis acid. So these compounds are the strong Lewis acid except AlF3. Why there is an exception here? AlF3 is an ionic compound. Okay. So it is not electron deficient in nature and it cannot act as a Lewis acid. Okay. But in case of boron, the order of acidic nature of trihalides is as follows. So all the halogens of boron you see, BF3, BCl3, BBr3, Bi3. Among these four, Bi3 is more acidic. Bi3 is more acidic in nature. Okay. BF3 is least acidic. So this order you have to study. It is very important. When BF3, why BF3 is least acidic? You see here, fluorine is an electronegative element. Fluorine is the first most electronegative element. Okay. And the size of the fluorine is very, very small. Okay. So size of the fluorine and the size of the boron, they are almost similar. Due to the similar size, the overlapping is very, very high. Due to the similar size, if boron tries to form the bond with this fluorine, because since they are having the similar size, this is the overlapping region, right? Both are having the same size of orbital. So overlapping area is very, very high. Overlapping area is very, very high, means you can find the electron density at the maximum here. Okay. So it is a kind of electron rich species. Since the electron density is very high here, due to the very high extent of overlapping, BF3 is called to be an electron rich, or we can say it is less electron deficient in nature. But in case of BCl3, the size of the chlorine is big. Means the size of the 3p orbital of chlorine is big compared to the size of the 2p orbital of fluorine. 2p orbital size is this. This is 2p. And this is 3p. 3p is little bit bigger in size. But boron is same, right? Boron is same. So this is the orbital of boron. But when you see the orbital, the size of chlorine, it will be like this. It will be like this. It is bigger in size. So here, if you see the extent of overlapping, it is very less. The extent of overlapping is very less. So due to the difference in size, the extent of overlapping is very, very poor. Extent of overlapping is very, very poor. If the extent of overlapping is very poor, the electron deficient nature is very, very high. Okay. So what they will do, BCl3 will try to accept the electron. And that's why BCl3 is more acidic in nature, but BF3 is least acidic in nature. Okay. So this is about the acidic nature. So now it's already 3:55. We will close the session now. So this is enough for today. So today we have discussed the group 13 elements introduction and the general properties and the trends and some of the general chemical properties we have discussed. And in tomorrow's class, we will continue this topic. We will continue this group 13 group, and then we will end up with, we will start with group 14. Okay, compounds are not there. So we can complete this lesson within 1 or 2 days. Okay, so all of you go home and try to solve questions from this topic. We will also solve in the weekend classes. Okay, so you guys also try to study this and solve this. So this lesson, this P block lesson is not included for your board exam. It is not there for NCERT. It is not there in NCERT syllabus. Okay, it is there only in JEE and NEET syllabus. So I think you cannot find this lesson in your book. I don't know which book you guys are using. So try to study this from the materials which you have from our side. Okay. So if you're having any doubts, you can ask me. If you are not having any doubt, then we all can meet up in the next session. No doubt? Okay then. Thank you, students. Thank you so much. Bye-bye.